Hi all, welcome to part 6 of the video lecture on counters. So we already seen what is counter and how this counting is happening, right? So especially for on bit counting is what we saw already, and the main concept we discussed is the something called that frequency division, right? So how a given T flip-flop or D flip-flop can divide the input frequency say by 2, right? The divide the frequency of the input clock by 2. So we observed that it is just the output of the T flip-flop is giving you a clock pulse that is of half of the frequencies that of the input. Now that output you connected to a second T flip-flop and you saw that it's further dividing that frequency by 2, right? So this is what we discussed so far. And in that way, so this is something we saw in the last video, last part of the video lecture. Given a clock signal of frequency some f hertz, how to generate another clock of frequency some f by 2 power k hertz. That means you want to divide the input frequency by some power of 2, like f by 2, f by 4, f by 8, like that you want to divide. You don't want to divide with some other number. It's enough to divide the input frequency by some power of 2. And that is whether the frequency division by some powers of 2 is it possible. So that is what we seen. So to achieve this we need k flip-flops cascader, right? Like k T flip-flops. Very simply same thing you can implement with the D or JK also. That variations also we saw. So for simplicity we can assume k D flip-flop. So what happened there is what was the conclusion? So this is your T flip-flop 0, and the output of this we denoted like a Q0. Then we have another T flip-flop 1, output we denoted as Q1. So this is your T input, right? Etc. Like that. How many T flip-flops you are having? Okay, or let me draw one more. So this is your T flip-flop 2, output we can denote by Q2. So this is the T input for all this. Maybe if you want you can denote like T0, T1, T2, whatever it is. That input to the flip-flop, yeah, etc. The last one, the T flip-flop. So as I started counting from 0, the last one will be flip-flop k minus 1, right? Like that. So 0 to k minus 1, totally T flip-flops are there. Now what you are doing, you are connecting all these T flip-flop in toggle mode. So what is toggle mode? So it will whenever the clock triggering happens, it will toggle, right? So toggle mode means T is equal to 1. So that will make the flip-flop toggle. So that is also by continuous toggling actually we are achieving this frequency division counting everything. So that is the idea. And now what about the clock signal? So that's interesting. Clock you will apply only to the first flip-flop, okay? So directly we will apply clock to the very first flip-flop. Now the output of this flip-flop is connected as the clock signal to this one. So for the second one the clock is nothing but the output of the first one. And similarly for this one again the second flip-flop is having a clock and that is being connected as the clock of this. So like that we will cascade the T flip-flops. And finally here also from somebody will be here, right? It's not shown, and that will its output will come as clock signal to that. So this is what we call as the asynchronous configuration, right? So what we are having here is a asynchronous circuit, sequential circuit. Synchronous sequential circuit. Why it is so? Because we are all the flip-flops are not synchronized by a common clock. Where in synchronous circuit it is like a same clock we will apply everywhere. But this is something different. So this is what we started our discussion with. The other one is very simple to understand. But this is something. This is also easy, but you have to observe it with the help of the timing diagram. And what? So that I hope you remember the timing diagram also. So let's quickly see the timing diagram. Okay, or we discussed already in the previous part, right? Hope you remember, right, how the timing diagram. Anyway, for a smaller case, I will take it further, because we want to observe the counting part also, right? That we will see. Anyway, this is a conclusion. So what we understood is K, T flip-flops, or other JK or T, everything will work, can cascaded, can divide input frequency by 2 power k, by 2 power k. So that is the understanding. And why it is so? Hope you remember again. So if I am applying a clock pulse here, say with some frequency, let's take a very small clock. So if I am applying a clock, something like this, say with some frequency f hertz, what will happen if you observe this output, I mean this Q0 output, this Q0 output, if you are observing, you will get a clock something of half frequency. Half frequency means the time period will increase, right? So this is of f by 2 hertz. Right. Similarly, if you are observing this Q1 output, you can see that this output of the second T flip-flop, it is nothing but a waveform which is of which is further half of the input frequency. So for second flip-flop, the input was like, so I can say that this is of frequency f by 2 by 2, that is f by 4 hertz. So the input clock is nothing but the output of the previous one, that is this one act as the input to this ff1, and it is divided further, right? Like that, every flip-flop will divide the frequency by 2 by 2 by 2, like that. And the last one, if you are observing the output, you will get a I mean something like this, right? So what I am concluding, it is of some value f by 2 raised to k hertz. Because here it is f by 2, here it is f by 2 square, then it is f by 2 cube, like that. The last one will divide the input frequency by f by 2 raised to k hertz. Divide by 2 power k. So this is the this is what we discussed in the previous video. Hope this concept is very clear. Now the question is, so clearly there is some division is going on, right? So we saw that the input frequency getting divided, and the least significant flip-flop, something like the first one divide by 2, second one divide by 4, like that. So, but how do we interpret this as counting? So we are interested in counting, right? In between we saw this frequency division as a particular application of it, but this is nothing but it's leading to counting only, and let's see how it is leading to that counting part. Okay, so for that, let's take a small example timing diagram. So here in this, here I discuss something where some k flip-flops are connected. I don't want it. Let's just to observe this counting part, I will be taking just 2 flip-flops, and let me check whether it's doing that counting or not. We already observed it for a single flip-flop, and there we observed that the state diagram 0 changed to 1 and 1 changed to 0. So there is a small counting like 0 to 1 and repetition of it. Now here, what about it? Okay, so for that I'm just assuming that 3 such no, it's enough to discuss 2 flip-flop case, and then you can generalize it to 3. So this is your flip-flop 0 with output Q0, and this is a T input, right? And this is your flip-flop 1 with output Q1. So let's just observe this, and I'm applying on input to clock, say with some frequency, right? Then I am taking output of this and applying it as the input clock to this, right? So, and you know it is of half the frequency, and then you know I am observing what is this Q0 and similarly what is this Q1, both I am observing. Okay, Q0 and Q1 wave. Okay, and what about this this T input? You have to connect it in the toggle mode. It should be 1. Fine. This is the configuration I am analyzing. Something we already seen only. I am just quickly telling you. So let's see that. So let's take the input. Let's take the input to clock. Suppose, or let me take it. Okay, fine, this is okay. Compared to the that one I shown, this is of very good frequency, right? Anyway, whatever it is, suppose this is the frequency of the input to clock. So this is how it appears. Okay, now this is my clock, right? I'm observing what is my Q0. Okay, what is my Q0? And you know that by default the Q0 by default we assume that it is in the lower, some low voltage, and during this transition, so this is something you have to highlight like this. So that positive, so the flip-flops will be triggered only during the positive edge or the rising edge of the clock, right? That is what we know already. Now we are observing what is that output of the first flip-flop and the second one. Okay, anyway, I taken it in detail. Yeah, fine. So what we are going to see is what will happen to this Q0 during this rising edge, and you know the flip-flops are connected in the toggle mode, so definitely during this rising edge it will toggle. So right now it is in 0, so it will toggle, it will go to high, and it will retain that till this. Now again the triggering happens, it will toggle further, it will retain like this, again toggle happens, it will retain like this, again toggle happens, it will retain like this, toggle, retain, toggle, retain, toggle, retain, toggle, retain, like that it will proceed. Fine, interesting. Now what about it? So the next thing is your Q1. So let's observe what about the Q1. Again Q1 is also proceeding in low voltage, and now you know Q1 is the output of the second T flip-flop whose input to clock is Q0. So you don't have to, please don't consider this original clock. Original clock is applicable only to the first flip-flop. Now for the second flip-flop onwards, the input to clock is the output of the first one. So Q1 is to be generated with respect to this Q0 as the input to clock, right? So look at the rising edge of this particular one. Okay, so that is happening like this. So it's somewhat 2 times of it, right? So that's how the time period is increasing. And now you can see that it's in low voltage. So now this second flip-flop triggered and it toggles. Now it continues till this. Now only it's triggered further. So it will toggle. Again it will continue like this. Now again triggered and toggled. It will continue like this, triggered and toggled. It will continue like this, right? So this is the idea. Now if I have one more, this Q1 will act as its clock, so that it will trigger little bit far away like this. Okay, so accordingly, you know, the output waves frequency will vary. So what are all the things we concluded? We saw that if this is of frequency some f hertz, you can see that this is of frequency f by 2 hertz. Why it is so? Because if you are looking at the time period of this one, if this is t, you can see that the time period doubles, right? So that frequency divided by 2. So because both the time period and frequency, they are inversely proportional to each other, right? So if time period is 2 times, frequency will be half of the original one. And here the time period is actually 4 times. It's now 4t. Accordingly, the frequency of this particular wave will be f by 4 hertz. So like that it will proceed. So this is what we've seen already. Okay, now let's observe the counting part. Okay, so that's interesting. So if you are looking at the counting part, so what I am saying that this Q0 and Q1, treating Q0 as the least significant bit and Q1 as the most significant bit, some kind of counting is happening on the background. Okay, so this is what I was trying to say. So let's take counting means some 2-bit counting like that. So I given a hint about it. So this output to Q0, so let me treat it as the least significant bit. Okay, and similarly this Q1 let me treat as the most significant bit, so that if I am observing at any time, so you have to observe like what is your Q1 and what is your Q0, like that. Okay, so like that I am observing. Initially I know both are 0 0. Okay, and now I am observing the clock. So now when this will change to the next state, that is only during the positive edge of the clock. Okay, so assume that the clock changes. Now as soon as the clock pulse came, you know, initially both were 0 0, right? So now when the first clock pulse came, you know, this Q0 alone toggled to 1, right? Not only Q0, Q0 toggled to 1, and as a result of this transition, I mean this Q0 is changing from low to high, again there is a positive edge, so that Q1 also toggled to 1. Is it clear? When the first clock, so now this clock is the input clock, right? So this clock here, clock, what I mean is the actual input clock. Okay, I mean what I can say about this clock, I mean, okay, clock to first flip-flop, like that. Okay, so in between also clocks are there, they are actually output of the previous flip-flop, but here the clock I am talking about is the clock's original clock signal, I mean this one. Okay, this one I am talking about. Now when the first clock triggering happened, you observe that both the Q0 and Q1 are changing to 1. Okay, so both are changing to 1. Why it is so? You know, Q0, it will change in every clock tick. Suppose, I mean, after that the next clock tick will come. That time Q0 will change to 0. You can see that it's changing to 0 during the next clock tick. Right. So again during the next clock cycle, immediately at the next clock cycle, Q0 will change to 1. So it's changing to 1, right? Again during the next clock cycle, Q0 will change to 0. Like that it will proceed. Why it is so? Because it's directly connected to the clock, right? So it will always toggle, at every clock tick it will toggle. Fine, but that is not the case with the Q1. So if we are looking at the Q1 will trigger during the first clock cycle, like this. Okay, it will trigger during the first clock cycle. Why it is triggering during the first clock cycle? Because during the first clock cycle, Q0 is changing to 0 to 1, and this 0 to 1 transition will act as a rising edge for flip-flop, the second flip-flop 1. Okay, and the second flip-flop triggered, and as a result this 0 changed to 1. Fine. Now when this I mean during the third original clock cycle, during the second original clock cycle, you know, Q0 is changing to 1 to 0, but this 1 to 0 is just a negative edge for this. Okay, I mean it's not going to trigger. Instead it will retain that one. Okay, it will retain that information because it's not the time for it to trigger, so this one will be retained. Okay, now you can see that again this Q0 is getting a transition from 0 to 1. 0 to 1 transition is what makes this Q1 toggle. Okay, so because this for Q1 the input clock is Q0 output, so that is getting, I mean during the next clock cycle Q0 is changing from 0 to 1. As a result our Q1 is going to change it to 0. So this 0 transition happens. That is because of this transition. Okay, now during the next one it simply retains. Okay, but this will toggle, right? So it will go like this. Again, if you continue this counting, this will toggle, this will toggle, this will toggle, this will toggle, 0 1, like that going. But here at this point this will toggle and then it will retain, right? Toggle, retain, like that it will come. Okay, again toggle and again retain. So if you continue 0 0, then you can see that after 0 0 both are changing to 1 1. Again both are like Q0 is changing to 0, this is changing to 1. Q0 is changing to 1, this is changing to 0, Q0 is changing to 0, this is retaining that 0, like that it will proceed. Fine. Yeah, sorry, here I made a mistake. What is that? It was 0 only. Fine. So that about it. But you don't have to take all this count into consideration because you know this is 0 0. What is 0 0? 0, then 1 1, 1 0, 0 1, again back to 0 0, right? And this pattern is actually repeating. Okay, if you are looking at again, it will repeat this pattern, right? The same thing is happening here. Okay, so you can draw the state diagram now. So if you are looking at the state diagram, you can see that the very first state of the flip-flop is, state of the flip-flop, hope you remember, the present output is what we call as a state. And this 0 0 is changed to what? 1 1 during the first clock tick. Now from this 1 1, it is further changed to 1 1, it is changing to 1 0 during the next clock cycle. So here what I mean is, this is my Q1, this is my Q0, again this is my Q1, this is my Q0, like that I am taking. So just like this, then 1 0, then again during the next clock cycle it's going to 0 1. Now again during the next clock cycle it's changing back to 0 0. So this is a typical state diagram, and you can see that this is actually what kind of a counting it is doing. You can see that this is your 0, then this is your 3, and this is your 2, and this is your 1. So it's a counter which is counting like a 3 to 2 to 1 to 0 back to 3. So it's a count down counter, right? From a bigger number, counting towards lower number. So it's a what kind of a counter it is? Basically it is a 2-bit counting, right? So only 2 bits are there in the counting. So I can say that it is a 2-bit count down counter. So by default counter we mean the up counter, but here what we are getting is a down counter. Okay, or how many different states it's gone through? 4 different states. Accordingly we can call it as its modulus is 4. Okay, so another name for it is modulo 4 countdown counter. Okay. So all those terminology, hope it is very clear to you. Yeah, that about it. Now in the next we will discuss there is a small thing called transient state maybe in the next video. Yeah, hope it is clear, right, how this counting is happening. It's a very very important observation. Now you should be able to generalize this for some 3-bit case, like for how a 3-bit counter is going to behave, 4-bit counter is going to behave. So by default when you are applying the clock as positive edge triggering, you can see that it's doing that down counting. Now the question is, if I am applying the negative edge of the clock, suppose that flip-flops are made in such a way that it's getting triggered during negative edge of the clock, will it count something different or same? Okay, so you can try it out. Okay, so I request all of you to try the same thing. You extend with one more flip-flop, 3-bit counting you try. Okay, 3-bit down counting will happen, you can check it, or modulo 8 counting will happen. Some 8 states you will get, but you should understand how those 8 states are coming. Okay, so work out and try it in your own way. And another thing you can try is change the clock to what? Negative edge triggered clock. I mean, and observe what is the output, 2-bit as well as 3-bit. You will see that if you are changing the clock to negative edge, it will work as a up counter or the default binary counter. Okay, so this kind of understandings are very important. So they can ask you any variation, that time you should be able to answer it. So that's why I am taking them in a very very detailed manner. Okay, yeah, thank you.